In this video, we'll talk about the integral test, which is our first method that can tell us either convergence or divergence of series without having to actually evaluate the sum of the terms. So this is going to use the fact that we talked about in the last video with the fact that if I have a series with only positive terms, all I have to do is show it's bounded to get that it is convergent. The integral test says the following. We're going to let our sequence, an, which is going to be the terms in our series, be some function of n, was defined by a function, where f is positive, meaning all the terms are positive, continuous, and decreasing on 1 to infinity. So I need the function to be going down towards 0, which makes sense. The only chance I have for convergence is if these terms actually go to 0. That was the nth term divergence test from the last section. Then I get two facts. If the improper integral from 1 to infinity of f of x dx converges, then the series converges. And conversely, if the integral diverges, then the series also diverges. Another way you might hear this said is the integral converges if and only if the series converges. As in, if I know that one thing converges or diverges, I then get the other thing then also converges or diverges. These are a back and forth sort of statement here. Unlike the divergence test, which was a one-directional statement saying if the terms don't go to 0, then it diverges. Here I have a back and forth going on where I can go in both directions and do either direction converges or diverges. We'll see how to use this here in a second. But why is this the case? So the main idea is that the improper integral is going to form a bound for my sequence of partial sums. And that is sort of the first picture here up on the left. The point is, the partial sums are adding up the areas of each of these boxes. Right, here's f of 1. So this a1 is 1 times f of 1. It's the first term in the series. Here's the second term in the series. Here's the third. Here's the fourth. Here's the fifth, and so on. So if you look at all these rectangles and add them up, at least the ones from 2 to n, the ones under here, adding up all those rectangles is definitely less than the improper integral of f from 1 to infinity. Why? Because that's going to encompass all of this area all the way out to infinity. Is all going to be in the improper integral. So what I have here is then the sum from n equals 2 to n of an is less than the improper integral for all n. Well, that just tells me that Sn is less equal to the improper integral plus a1, because I'm missing a1 from that first sum, and that's a number. This tells me that this is a bounded sequence, provided the improper integral converges to a number. I don't have to find that number, I just have to know that it does converge to something. And if it does that, this here is some number, whether I can find it or not, that is an upper bound for my sequence of partial sums. Therefore, my sequence of partial sums is bounded, which means it converges. So that's the one direction. For the other direction, the idea is similar, except now I know that my partial sums are going to be bigger than the integral, because the area they take up is more than what's under the function. So in this case, the integral from 1 to n of f of x dx is less than Sn. But I know as n goes to infinity, if I'm assuming the integral diverges, this diverges and goes to infinity as n goes to infinity, and this is bigger than it. So it must also go to infinity and so diverge. So I can sort of use the integrals and the sums interchangeably to figure out if things converge or diverge, and that's the point of this theorem. If it's a nice function, I can just integrate the function and see what happens there, and that'll tell me if it converges or diverges in the series form as well. And the main way this is applied is with the convergence of P series. So just like P integrals, a P series is the sum from n equals 1 or 2 or some lower endpoint to infinity of 1 over n to the p. And if I want to know when these converge or diverge, the integral test tells me to look at the integrals instead. So by the integral test, does the integral from 1 to infinity of 1 over x to the p dx converge or diverge? Because based on my test, these are the same answer. Well, this converges for p bigger than 1, and it diverges for p less equal 1, and so the same is true for the series. So these here will be important facts to know when we're talking about a lot of the other tests later on, that these are your sort of base cases. These are things that you know converge and diverge that you can then use in all the other tests. So for example, show that the sum from n equals 2 to infinity of 1 over n squared converges, but 1 over n diverges. This is again just the integral test, or the fact that we know things about P series. The point being, integral from 1 to infinity of 1 over x squared dx converges, but 1 to infinity 1 over x dx diverges because that's a log. One other point to make here, this integral you can evaluate, right? This integral here evaluates to 1. However, that does not mean the series equals 1. It turns out that even though that integral is 1, if you look at the actual sum, this time we'll go from 1 to infinity because I know this one off the top of my head. This is pi squared over 6. So it's not 2, which would be if you had added 1 to that integral, but it's some other number. But it does converge, and that's what this test tells us. It doesn't tell us what the value is. Tells us that it converges to a number, and that's the fact that we get out of this. We don't get the value from the integral test. We just get does it converge or does it diverge. And it's important to have that distinction separately when we're going through things. So there's our first test. It's the integral test. It allows us to figure out if series converge or diverge without needing to actually evaluate the sum of the series. And that's what we'll see going forward with the rest of these tests, is there are ways to tell about convergence or divergence without evaluating them. And they don't even give us the result. Even if this gives us a number, it does not give us the actual value of this series. You'd have to get that by some other numerical way or some other argument that is not one of these tests.